Okay, so we are continuing where we left off with the illumination problem. And essentially, what I want to do is stop at this step right here. So this is where I went astray in terms of solving. So let's go ahead and erase everything below that. We're still trying to find our critical value and try to solve for when this equation is equal to 0. So it is correct that if I want to solve this fraction equal to 0, I need to just look at the numerator. So I'm just looking at when the numerator is equal to 0. And now, to save myself a little trouble, what I'll do is I will express this as x cubed equals 3 times 2 minus x, 10 minus x quantity cubed. And now I will take the cube root of both sides. So this is what will make my life easier. On the left-hand side, I'll have x, and on the right-hand side, I'll have the cube root of 3 times 10 minus x cubed to the 1/3, but that's, of course, just going to be 10 minus x. Okay, so I'll have x is equal to the cube root of 3 times 10 minus x. We can go ahead and distribute this. So we'll have the cube root of 3 times 10 minus the cube root of 3 times x is equal to x. We're going to add cube root of 3 times x to both sides. And we'll have 1 plus the cube root of 3 times x is equal to the cube root of 3 times 10. And now we'll divide both sides by that coefficient. And we'll get our answer for x. So x is equal to the cube root of 3 times 10 divided by 1 plus the cube root of 3. So this is our critical value. And we would just need to verify that, what remains is verifying that the illumination attains a local min at this critical point. Okay, and so for this problem, I think the main focus is the setup, right? So figuring out your equations, interpreting the wording of the problem.
It's
12:15. Right? Figuring out your domain. So I'm going to actually stop right here and just let this be our solution. So our solution is going to be that to minimize the illumination, we should place the object cube root of 3 times 10 divided by 1 plus the cube root of 3 feet from the strong light source. Okay, and we can notice kind of just by looking at this number, this will indeed be in our domain, because the cube root of 3 is about 1.4. So the cube root of 3 is approximately 1.4. So we have essentially, this answer is approximately 1.4 times 10 divided by 1 plus 1.4. which is 14 divided by 2.4, which is definitely less than 10. Okay, so 14 divided by 2.4, it's like 5.8. It's about 5.8. So it's actually not going to be, the optimal place is not in the middle of the two light sources, but it's a little bit closer to the weak light source. Okay, all right, good. So now we have one last problem here that we need to go back and look at. And it's actually, we almost finished with this problem. This is a problem involving the veins and the resistance of blood based on the angle between the main vein and the little smaller vein. Okay, so in class we showed that the minimum is going to occur when cosine of theta is equal to this fraction here, this ratio. And so we've got this one last problem, which is to find the optimal branching angle. And in this case, optimal means what's going to result in the least resistance. Okay, so find the optimal branching angle when the radius of the smaller blood vessel, so the radius of the smaller blood vessel, remember, was denoted by R2, is 2/3 the radius of the larger vessel, and the radius of the larger vessel was R1. So our condition here is essentially that R2 is equal to 2/3 of R1. And so we want to find theta. So our goal, let's go ahead and write it down. So our goal is to, for what theta is cosine of theta equal to R2 to the 4th power divided by R1 to the 4th power, given that R2 is equal to 2/3 R1, because this theta is where our resistance function is minimized. Okay, so we just need to plug in that R2 is equal to 2/3 of R1. So we'll have cosine of theta is equal to 2/3 R1 quantity to the 4th power divided by R1 to the 4th power. And we can expand the numerator. So we'll get 2/3 to the 4th power times R1 to the 4th power divided by R1 to the 4th power. The R1 to the 4th power and the numerator and denominator cancel each other out. And we're left with just 2/3 to the 4th power, which is going to be 16 over 81. And now 16 divided by 81 is approximately 0.19753. So we need to find for which theta is cosine of theta equal to 0.19753. Okay, so I'm actually going to go up here to the side here, and if we're trying to solve for theta, cosine theta equals 0.19753. Given to the constraint, I believe the constraint we had was that theta needs to be in between 0 and pi. We are essentially asking for cosine inverse of 0.19753. Okay, and that gives us 78.60749 degrees. We use a calculator to compute that, and so we round that up to 79 degrees. So the optimal branching angle, 79 degrees. All right, so if this is 90 degrees, then the optimal branching angle would be something like that. Which is pretty interesting, because I would have thought it would have been, you know, more like that. But nope. 79 degrees is the optimal angle. Okay, Thank you.